Hey everyone, I hope you're having a great SUSECON Digital 22. Today, we're going to present an exciting solution called the Edge to Cloud Data Engineering Platform. We'll show you how the best of breed technologies from Hewlett Packard Enterprise and SUSE come together to deliver a solution to operationalize machine learning for our enterprise customers. Here's a quick look at the agenda. First, we'll walk you through the challenges in operationalizing machine learning. We will present an edge to cloud architecture for machine learning. We will walk you through the 4 foundational capabilities such a platform should provide, a real implementation of the edge to cloud data engineering platform, and lastly, an end-to-end workflow of how such a platform enables continuous learning for machine learning models. And then lastly, we'll wrap by walking you through some of the key technologies that help us realize such a solution in production. I'm Rajesh Vijayarajan. I'm a distinguished technologist with Hewlett Packard Enterprise. I work for a group of global sales engineering, and we support some of our largest accounts across the globe. I take lead on a variety of emerging technologies. I have a special interest in edge computing and edge to cloud architectures. Today, I'm joined by a good friend, Brian Fromme from SUSE, who takes lead on the alliances with HPE. Now, let's take a look at the typical challenges an enterprise would run into when operationalizing their machine learning. Firstly, there could be many models, many revisions of those models, and many sites to which these models need to be deployed. So how do you securely onboard them, and how do you monitor them once they're in production? The typical set of skill sets required for handling such a deployment span from data engineering, data science, and ML Ops. These skills are hard to come by. And then there's the ever-increasing complexity and evolving nature of the tools and frameworks that are put to use to build such a project. Now, how do you keep up? There's a lot that is learned only after a model is put into production. You may run into issues like drift and the lack of explainability or interpretability of your machine learning models. You may also have to deal with societal issues like dealing with bias and fairness. It's easy to start in the cloud, but is it truly scalable and sustainable once you expand into production? And then the lack of automation may also mean that you have humans in the loop for most of your deployments, which can either slow them down or be very, very error prone. Let me bring another perspective. There's a lot of fascination around machine learning frameworks when it comes to machine learning. But in reality, the machine learning code is not even 10% of the whole ecosystem that is required to put a model into production. There's a big pivot towards data-centric AI. This means there's a larger, greater emphasis on the quality of the data that goes into building your machine learning models. So as you can see, the data science piece of it is a very small fraction. Vast majority of it is on MLOps and data engineering. And this is the opportunity for both HPE and SUSE to play in the market. Now, let's take a look at what an edge to cloud architecture for machine learning looks like. The cloud is the host of vast majority of compute and storage, and here is where typically the machine learning models are built or the production of AI happens. But then the vast majority of the consumption of AI, or what are called as inference, happens at the edge sites, which are closer to the source of the data. So the typical set of interactions required between these sites is the cloud having the ability to update the apps and the models that run on the edge sites, and the edge sites in return have the ability to ship data selectively back to the cloud to facilitate what is called as continuous learning or continuous improvement. So the cloud has to provide the capabilities to handle edge devices, apps, and data. It has to provide the infrastructure for operationalizing your machine learning, and then it also has to host a data lake or a lake house against which you can spin up training environments to actually explore the data and build new models or update existing models. The edge, in turn, has to provide the ability for low latency ingest of the data, provide capabilities for pre-processing or fusing of sensor data. It should have the ability to present real-time dashboards, perform real-time inference, And then we also see a subset of use cases where the edge may even have to host the training infrastructure, in which case the data is not exchanged over a wide area network, and you may have to use tools like federated learning or swarm learning to improve models across all your deployments. Now let me touch upon the 4 foundational capabilities that such a platform should provide. Firstly, the app orchestration piece of it. We believe that all software components that you deploy through the edge to cloud continuum need to be deployed as microservices, and the de facto standard for orchestrating these microservices today is Kubernetes. And then you need what is called as a data orchestration capability. This is to do with how do you consistently handle the data for these applications at your edge sites, and how do you bring in the capability to selectively ship just the required minimum amount of data back to the cloud from your edge deployments. The third pillar is all the tooling that you need to sort of operationalize your machine learning. These are the set of tools that will bring in scale, visibility, the required agility, and will help you stay compliant when they're in production. And then lastly, you have the edge application management, where you need the ability to treat your edge as an immutable infrastructure. And here is where an industry best practice called GitOps is applied, where as a Git repository, which is treated as a single source of truth for all your deployments across your edge sites. Humans are not allowed to either on-site or even remotely make changes to an edge site. Everything is orchestrated through a set of tools to offer the hyperautomation that you need to securely deploy updates. Now, let's take a look at a real implementation of such a platform. The HPE Edge to Cloud Data Engineering Platform is built on the following 4 components. Firstly, for the app orchestration piece, we use the HPE Ezmeral Runtime Kubernetes distribution in the cloud, and then we pair it with the SUSE Rancher Kubernetes distributions for the edge sites. The data orchestration capability is provided by the HPE Ezmeral Data Fabric, or more popularly known as the MAPA file system. It provides capabilities like a global namespace and also multi-persona storage, wherein you can configure files, volumes, tables, and streams backed by the same file system. And the data fabric is the default persistent storage provider to all the microservices that are deployed on this architecture. And this enables us to asynchronously handle the data management behind the scenes. The third piece is the MLOps tooling, for which we use the HPE Ezmeral ML Ops suite. This provides some of the most popular open source projects like Kubeflow, MLflow, Jupyter Notebooks, Airflow, and the popular machine learning frameworks, all packaged into one. Lastly, for the edge deployments, we use the Rancher Fleet solution, which provides the GitOps capability that I alluded to in the previous slide. This is also coupled with Jenkins, which provides the ability to deliver the hyperautomation around packaging of containers and also generation of deployment manifests. Let's look at a typical deployment pattern of such a solution. There are 2 types of edge sites. One is what is called as the far edge. Think of these as typically the data acquisition devices, which are mostly performing the I/O and hence don't have a high availability aspect to it. But there's still a need for us to handle the data pipelines that need to be orchestrated on this device. The near edge is a more capable edge site, which has the ability and the need to run microservices in a highly available manner. And here is where we also land an instance of the Ezmeral Data Fabric. The cloud has a data lake against which training environments are spun up, which gives the ability for the data scientists to go explore the data, as well as generate new models or update existing models. And then there is the GitOps and the CI/CD aspects of the solution, which enable you to perform some sort of hyperautomation to effectively package the updates and deploy them in a scalable, secure manner. Now, let's take a look at a very interesting use case of putting this platform to use: continuous learning or continuous improvement for your machine learning models. So here's a typical end-to-end workflow for the continuous learning process on top of this platform. It begins with the day one machine learning development. And how this is done is by usage of tools like Jupyter Notebooks, where the data scientists can run a variety of experiments on the data and generate models in the process. We also have specialized tools like the Determine.ai solution, which can make it easy for you to handle experiments, perform hyperparameter search, and network architecture search, and so on. We provide the necessary integration with MLflow, which provides the abilities to track all the metadata from your experiments and also create what is called as a model registry. The art of training a model is a very empirical process, right? So typically to build a model, you may run a few hundred experiments. So instead of having to eyeball the screen to determine the best model when you're done with your experiments, MLflow makes it easy by tracking all the metadata and presenting a pretty dashboard. So after the experiments, you can look through the MLflow dashboard and sort your experiments based on a variety of criteria, which make it easy to pick the model of choice. When a model is promoted to be in production, you can actually determine that model by using the MLflow API. And this is how we build the automation around it. So once a model is promoted to be in production, Jenkins would have the ability to query using MLflow API to determine the path to the model that was promoted to be in production. Once it determines the path, Jenkins will download this particular model and then inject it into a container image to sort of generate the inference engine container that encapsulate the model. Then there is a second workflow which will generate the deployment manifests that are required to deploy this container onto an edge site. It is at this step that the GitOps process, which is the Fleet solution, takes over. Fleet has been configured in two ways. Firstly, to monitor a Git repository to which the edge deployment manifests are checked in. And secondly, the Fleet is also configured with cluster groups, which enable Fleet to either handle the deployment to all the clusters or to a select group of clusters. So the moment somebody promotes a model to be in production, Jenkins takes over and packages that model to be an inference engine container and generates and checks in the deployment manifests that are required to deploy that container. Fleet, which monitors this Git repository, will now completely handle whatever it takes to eventually deploy that container to all the configured edge sites. And lastly, the Ezmeral Data Fabric that has been deployed to all the clusters at the edge sites provide the ability to asynchronously transfer data of interest, such as outliers or model metrics, so that the data engineers can work on that next version of the data set, mostly focused on scenarios on which the model didn't perform well. And this process essentially continues.
Thanks so much, Rajesh. That was a really fascinating look at the implementation of the data engineering platform and the machine learning needs that development organizations need to push modern workloads to the edge. So let's talk about key enabling technologies that build up the application infrastructure at the edge. So first, we're going to look at the operating system level. So SUSE has developed an operating system called SLE Micro. It's really the same operating system technology inside SLES, our SUSE Linux Enterprise Server, but it's designed and tailored for the edge environment. So let's talk about a few aspects of how we've designed and tailored that operating system. So SLE Micro is a small footprint and enterprise grade. And by enterprise grade, it's not only SLES, the actual same well-tested, well-known SUSE Linux enterprise server, but it's designed with an immutable file system. So it's an immutable operating system. It's difficult to tamper with. So that's a key aspect of how we build another aspect of security into the operating system. It's mission critical. So we know that edge devices are part of services that are important for an enterprise to run their business. So these are mission critical services. So not only the immutability that we'll go into a little more detail on, but there are other aspects of security like SE Linux that are built into the operating system. So a customer can pick and choose from security stacks that make sense for them to really design the security as fits with their enterprise governance and policy. It's a low maintenance operating system, so it's really meant to be self-managing. It takes care of updates and really doesn't need to have an operator inject our work into the operating system while it's running. So that's a key aspect of the low touch or zero maintenance approach to an edge environment. And then finally, it's designed for a container or virtual machine environment. So we do a lot of work to make sure Kubernetes is something that is supported and runs on top of SLE Micro, and same with virtual machine environments. So we'll talk about those as well. So let's touch a little deeper on the immutability aspects of SLE Micro. Immutability really refers to a read-only file system. So somebody can't go and tamper with the file system as the operating system's running. We also allow patches and updates to be applied to the system, and we do that through a rollback and snapshot model. So we use an AB file system where A is the current running operating system and B is where transactional updates get applied, and we'll talk a little bit more about that in a moment. And so those are done in an immutable snapshot way so that then those updates get applied and we can roll back if anything goes wrong with those updates. The workloads I mentioned can be containerized or virtual machines. We can also add packaged software as well, but really it's designed to be for modern workloads that are leveraging containerized applications or workloads that are built into virtual machines. So we'll touch on both of those aspects in a moment. And then finally, because we expect customers to be building containerized microservice-oriented applications, we have something called the SLE-based container image. And this is all part of the security model. We want customers to be able to start with SLES technology as the base for their container implementations, and then know that they're getting standard components from SUSE that are well supported, that are secure, well tested, and that builds up more trust and security into the application stack. I mentioned the immutable and transactional approach to the way the operating system is designed. So from the read-only file system, when we go to apply patches for things like security or bug fixes, then those come as an atomic update or a transactional update. And those transactions happen all at once as opposed to separate packages that have dependencies like in a normal Linux packaging model. And when those packages are applied, they're applied to a new snapshot of the file system in Btrfs. And then the operating system will reboot to that new file system in snapshot. And if all of that works correctly, that's the new immutable file system that will be marked as the A file system. If that doesn't work, then we roll back to the previous version of the A file system. So we know that the operating system then can kind of take care of itself and apply updates in an unattended manner. I mentioned Kubernetes as one of the pieces of the layers on top of the operating system where we want to be able to land applications. So Rancher has designed something called K3S, which is a lightweight, edge-tailored version of Kubernetes. It's a full Kubernetes implementation, but it's designed to run in smaller footprint machines, and it's designed to run in a more supportable way for a single node of a Kubernetes cluster. And so that's great for running on very small footprint machines all the way down to something like a Raspberry Pi. And that's very typical for our edge environment where we have devices of all sorts in the operating environment in retail stores or healthcare or a number of other markets. We also have a component called Longhorn. Longhorn is interface to block storage, and we use that to allow customers to quickly get access to local file system storage data. Longhorn can also interface to other file systems that are non-local. HPE does a lot of work with CSI drivers for access to things like Primera and Nimble and other storage systems. So that gives customers a wide range of storage choices when they're implementing their applications at the edge so that they can still leverage enterprise storage capabilities in, say, an area near the edge device, maybe a closet cluster of some sort. SUSE Rancher also has a component called Fleet, and Fleet is a key component of managing the clusters of Kubernetes at the edge. And Fleet really is designed around GitOps and focuses on CI/CD. So that's part of the process that development needs to push code to the application infrastructure on a regular basis. That's part of what we're doing with our digital transformation for our edge applications. But Fleet is also designed to operate at scale. So one of the challenges that we have in any kind of environment, let's talk about retail. If we look at a customer like Walmart or Walgreens, they have thousands of stores just in North America alone. And those thousands of stores, each store may have hundreds of devices in them. Those devices are cameras and scanners and point of sales devices and sensors and all kinds of elements that make up the new digital service model in the store. And those hundreds of devices times thousands of stores means we could have potentially tens of thousands or even hundreds of thousands of Kubernetes instances to manage. So Fleet is designed to deal with scale at that level. So that's a key aspect of what we need to manage an edge application infrastructure for a large corporation. SUSE Rancher also has a component technology called Harvester, and Harvester allows us to bring virtual machines into the Kubernetes environment itself. So what's great about that is it allows us to think of Kubernetes as the application infrastructure from which we manage the applications themselves, whether those applications are containerized or they're virtual machines. Harvester leverages a Kubernetes technology called KubeVirt, and that allows Rancher, the management server, to manage the Harvester implementations as if they were containers themselves. So we can look at the virtual machines and containers across our Kubernetes landscape and manage all of those from a Kubernetes perspective. SUSE also creates a software component called SUSE Manager, which is really focused on managing the application infrastructure at the operating system level. That's another piece of the security model that we need. So we need to be able to identify and manage the software components at the operating system level. And SUSE Manager does that not only for SUSE Linux, but also for other enterprise Linux systems. And that allows customers the flexibility to work across their IT landscape, whether it's infrastructure inside their data center, maybe it's HPE GreenLake infrastructure that's done on premises, maybe it's infrastructure that's in a public cloud, or through some other mechanism, other managed service kind of providing environments. All of those are different, potentially different environments that customers might pick and choose different operating systems, and SUSE Manager can manage all of those. SUSE Manager at the edge is really focused on edge needs. In particular, we add some capability like image building. So customers often, when they have an edge tailored device, they build up that device. Maybe it's an NVIDIA Jetson or some other device that's capable of doing some GPU processing for machine learning, and they may want to build a custom environment on top of that. They still want some of the key characteristics that we've talked about, like enterprise security and support for the plethora of machines that they're building and supporting. So SUSE creates something called Open Build Service, as well as we leverage Kiwi technology to allow customers to build from well-known packages that are in SUSE Linux to create custom images of their own. So these are things that customers can do with SUSE together to build up their own versions of operating systems in a supported way. And then finally, we do a lot of work with HPE GreenLake, as we've talked about in the data engineering platform world, but we also work with the key security technology that HPE is developing called Project Aurora. So let's talk a little bit more about that. Project Aurora is meant to be security from the hardware infrastructure up into the software and workload stack. And so this is a graphic that kind of depicts those levels, and we'll just touch on them briefly. You may recall that years ago, software security really focused on data center and securing perimeters, and we wanted our machines within the perimeter to be secure, but we didn't worry so much about supply chain. We'd get software from a vendor and we'd write some software and we'd put it all on those machines. Today, we've noticed that software supply chain is now something that's becoming vulnerable, that customers need to be concerned about in terms of their security. So we need ways to attest to the componentry that we're pulling together into our software stack, whether that's firmware, whether that's operating system, whether that's third-party software, whether that's infrastructure software like Kubernetes, or that's workloads that we're developing. And that's the design model for Project Aurora, that there are components that deal with the security at each of those layers that we just discussed. So, first of all, thank you very much for joining us on this little machine learning and data engineering platform road trip. It's been a fun conversation. We talked about several interesting things. We talked about HPE GreenLake as it applies to machine learning and how HPE is helping customers with that aspect of their digital transformation and edge development. We talked about the data engineering platform as a piece of that design for how HPE designs an architecture for developing and deploying the infrastructure that makes this all succeed for customers. And we talked about how SUSE edge technologies apply into the data engineering platform and into HPE GreenLake to bring solutions and application infrastructure together that help it make it easier for customers to deploy their applications into a well-known and secure application infrastructure stack. So thanks again. Thanks to Rajesh, and thanks for your time today. And I hope you enjoy the rest of your SUSECON experiences.